This is a video from section 7.5. I'm going to be doing problems from the Stewart Calculus textbook, 9th edition. And with that, let's take a look at problem 21. Suppose I had the integral of cosine cubed x divided by cosecant x dx. Now, when I look at a problem like this, cosines and cosecants don't go very well together, but cosines and sines do, right? And if we remember, we have the following. 1 over cosecant x is the same as sine of x. Okay? And so I could rewrite this integral as cosine cubed x times sine of x dx. Okay, now this can be done by u substitution. So I'm going to let u equal cosine of x. Du is negative sine of x dx. And so sine of x dx is negative du. And so this is negative the integral of u cubed du, which is negative 1/4 u to the 4th plus c. But remember, u is cosine of x. And so this is equal to negative 1/4 cosine to the 4th x plus c. And that's how we do problem number 21. So let's take a look at problem 22. Suppose we had the natural log of 1 plus x squared dx. This is an integration by parts problem, okay? And so the way I'm going to attack this is I'm going to let u equal natural log of 1 plus x squared. dv is equal to 1 dx. So du, if I apply the chain rule, is 2x divided by 1 plus x squared. Because remember, the derivative of 1 plus x squared is 2x, right? So du is 2x over 1 plus x squared dx. And v is equal to x. And so the natural log of 1 plus x squared dx is uv, which is x natural log of 1 plus x squared, minus the integral of 2x over 1 plus x squared times x dx. So it should look something like this. And so the integral of natural log of 1 plus x squared dx is x natural log of 1 plus x squared minus the integral of 2x squared divided by 1 plus x squared dx. Now, I'm going to show you guys a little trick here. So we get x natural log of 1 plus x squared minus 2 times the integral of x squared divided by 1 plus x squared dx. Now, the way I'm going to do my long division is as follows. So I'm going to add 1 to the numerator, but then subtract 1. So it's kind of like adding 0. But I want you to watch what happens when I do that. I get x natural log of 1 plus x squared minus 2 times the integral of. Now, if I split off that fraction, I get x squared plus 1 divided by x squared plus 1, right? Minus 1 over x squared plus 1 dx. Just like this. And so I kind of use this idea. Like if I have a minus b divided by c, this is a over c minus b over c. So I could split the fraction. But remember, x squared plus 1 over x squared plus 1 is 1. So I get x natural log of 1 plus x squared minus 2 times the integral of 1 minus 1 over x squared plus 1 dx. And so this is x natural log of 1 plus x squared minus 2 times the integral of 1 dx is x. The integral of 1 over 1 plus x squared dx, or 1 over x squared plus 1 dx, is the arctangent of x. And then I add c. And then all I have to do is distribute that negative 2 inside. And so the integral of natural log of 1 plus x squared dx is x ln of 1 plus x squared minus 2x, right? And then a negative times a negative is a positive. So I'm going to get plus 2 times arctangent of x plus c. And that's number 22. If we take a look at 23, suppose I had the integral of x secant x tangent x dx. So I'm going to let u equal x, and I'm going to let dv equal secant x tangent x dx. So I'm thinking integration by parts because the first thing I'm going for is u substitution. But if you look at the first one, right, if we compare it, right, and I get down to the integral of cosine cubed x times sine of x dx, I know that the derivative of cosine is almost present within the integral, right? And that's why u equaling cosine of x makes sense. And doing u substitution for this problem makes sense. But if I compare that to problem 23, I don't know how to get rid of the x's in terms of u's, right? So you have to have the derivative present in the integral. And it's not. And so therefore I'm doing integration by parts. I'm going to try that. But I can think of a function whose derivative is secant x tangent x, right? So I'm going to let u equal x, and I'm going to let dv be secant x tangent x dx. So du is dx, and v is secant x, right? And so the integral of x secant x tangent x dx is x secant x minus the integral of secant x dx. And I'm done. And so this is x secant x minus natural log of the absolute value of secant x plus tangent x plus c. The ultimate check is if I take the derivative of this whole entire function, I should get x secant x tangent x back. That's how you can actually check to see if we did it right. Okay? And that right there is how you do problem 23. Let's take a look at problem number, we'll go for problem 24. So this one's a definite integral, okay? So we get the integral from 0 to square root of 2 over 2 of x squared divided by the square root of 1 minus x squared dx, okay? And so this is classic trigonometric substitution. So I'm going to draw a picture here, okay? Now, the hypotenuse, here's theta, by the way. The hypotenuse is 1. The side opposite angle theta is x. And then over here, we have the square root of 1 minus x squared. So I always default to the triangle. Okay, now, so if I take the opposite over the hypotenuse, I get sine of theta. Okay? So dx is cosine theta d theta. And then one more step here, or two more steps. The square root of 1 minus x squared is equal to cosine of theta. Because if you want, you can think of that as over 1. So adjacent over hypotenuse is the cosine, right? Now, we almost have all our substitutions, but we have one more thing to take care of, and that's those limits. So, when x is 0, can we agree theta is 0? Right? Because we need the limits in terms of theta. When x equals the square root of 2 over 2, we have sine of theta equals the square root of 2 over 2. And so, therefore, theta is going to be pi over 4. And so this is the integral from 0 to pi over 4. Okay? Now, x squared is sine squared theta. So we get sine squared theta. And I'm going to divide by. Square root of 1 minus x squared is equal to cosine theta. And then I'm going to multiply by dx, which is cosine theta d theta. Straight substitution, okay? And do you guys understand over here, when x is 0, theta is 0, so keep in mind, I'm saying sine of theta is 0. I'm making my substitution over here. And so, therefore, I'm asking sine of what is 0, and theta is going to equal 0. And so back here, notice how the cosines cancel, and we get the integral from 0 to pi over 4 of sine squared theta d theta. Okay? Now, this is a power-reducing formula. You get the integral from 0 to pi over 4 of 1/2 of 1 minus cosine 2 theta. Here, let's rewrite that a little better. D theta. Okay. Now I'm going to pull the 1/2 out in front. So this is 1/2 the integral from 0 to pi over 4 of 1 minus cosine 2 theta d theta. So this is 1/2 of theta minus 1/2 sine 2 theta evaluated from 0 up to pi over 4. I love definite integrals. The fundamental theorem of calculus is very important, okay? And so here you get 1/2 of pi over 4 minus 1/2 sine of pi over 2, right? Because remember, 2 times pi over 4, right? 2 goes into 4 twice, and you get pi over 2. And sine of pi over 2 is 1, and so we get 1/2 of pi over 4 minus 1/2. And I'm done. And that right there is problem 24. if we take a look at 25, suppose I had the integral from 0 to pi of t cosine squared of t dt. Now, what I would do is I would have the integral from 0 to pi of t times 1/2. I would use the power reducing formula again. So it's 1/2 of 1 plus cosine 2t dt. And so this is the integral from 0 to pi of 1/2 t dt plus the integral from 0 to pi of 1/2 t cosine of 2t dt. Okay, now I'm going to take this in pieces. So let I sub 1 equal the integral from 0 to pi of 1/2 t dt. It's just kind of a nice way to organize our thoughts. And so this is 1/4 t squared evaluated from 0 to pi. And so the answer here is pi squared over 4. Okay. Now, let I sub 2 equal the integral from 0 to pi of 1/2 t cosine of 2t dt. Yeah. Okay, and we could keep the 1/2 out in front of the integral or inside. It really doesn't matter. Okay, so from here, I'm going to let u equal 1/2 t. And dv is cosine of 2t dt. And so du is 1/2 dt, and v is 1/2 sine of 2t. And so I sub 2 is 1/4 t sine of 2t. And we're going to evaluate this from 0 to pi. And then I'm going to subtract off 1/4 the integral from 0 to pi of sine of 2t dt. Now, if you guys remember, sine of 2 pi is 0, and sine of 0 is 0. And so this term, this first term, is going to go away. And so you're going to be left with negative 1/4, right? And then it's the integral from 0 to pi of sine 2t. dt. So this is negative 1/4 times negative 1/2 cosine of 2t. And we're going to evaluate this from 0 to pi. And remember, negative 1/4 times negative 1/2 is 1/8, right? And so we get 1/8 times cosine of 2 pi minus cosine of 0. Well, that's equal to 0, interestingly. Okay? Now, I'll leave it at that. Yeah, so that's equal to 0. And so, therefore, if we go back, the integral from 0 to pi, of t cosine squared t dt is I sub 1 plus I sub 2. But that's equal to pi squared divided by 4. Because if I'm not mistaken, we got 0 both times for I sub 2. And That's how we do problem 25. Let's take a look at 26. Suppose we had the integral from 1 to 4 of e raised to the square root of t divided by square root of t dt. Okay? Now, I'm going to let u equal the square root of t. du is 1 over 2 square root of t dt. I always go for u substitution whenever possible. Okay? And so 1 over the square root of t dt is equal to 2 du. So I just multiply both sides by 2. Now, when t is 1, u is 1. When t is 4, u is the square root of 4. So you see I'm plugging it in up here, which is equal to 2. And so this is the integral from 1 to 2 of 2e to the u du. Okay? And this is 2e to the u evaluated from 1 to 2, which I'm going to pull the 2 out. If I plug in 2 for u, I get e squared. If I plug in 1 for u, I get e. So I get 2 times the quantity e squared minus e. Now, your instructor may want you to factor out an e. So if you factor out the e, you get 2e times e minus 1. So you want to check with your instructor which one your instructor would prefer. On 27, suppose we have the integral of e raised to the x plus e to the x dx, which is the integral of e to the x times e raised to the e to the x dx. So I just happen to notice the following. The derivative of e to the x is e to the x, right? So in my mind, I'm thinking let w equal e to the x. So dw is e to the x dx, right? So this is equal to the integral of e to the w dw. But this is e to the w plus c. But remember that w is e to the x. So therefore, the integral of e raised to the x plus e to the x dx is e raised to the e to the x plus c. And I'm done. So that was 27. So let's take a look at 28. Suppose I had the integral of suppose I had e to the x over 1 plus e to the 2x dx. So what I would recommend is maybe thinking about it this way. I have e to the x over 1 plus e to the x squared dx. And so this is going to be a classic u substitution. Let u equal e to the x, and notice how the derivative is present. So du is e to the x dx. And so we get the integral of e to the x over 1 plus e to the 2x dx is the integral of 1 over 1 plus u squared du, which is arctangent of u plus c. But u is e to the x, and so we get arctangent of e to the x plus c. And that right there is problem 28. If we take a look at problem 29, so suppose I had the following. Suppose I had the integral of arctangent of square root of x dx. Now, I would do this by probably a couple ways you can do this. Let's try to get rid of the radical. It's a nice technique to know, you guys. So if I let u equal that square root of x, now let's square both sides. And so u squared equals x, completely legal. So I'm going to differentiate, and so I get 2u du is equal to dx, okay? And so this is the integral of 2u arctangent of u du. Integration by parts. So I'm going to let w equal arctangent of u. U is already taken, so I can't do it twice. dv is equal to 2u du. So v is u squared. dw is 1 over 1 plus u squared du. So we get the integral of 2u arctangent of u du is, so I get u squared arctangent of u minus the integral of u squared over u squared plus 1 du. And so this is u squared arctangent of u minus the integral of u squared plus 1 minus 1 divided by u squared plus 1 du. And so this is u squared, same technique. And then I'm going to split off the fraction. If you guys remember, I get 1 minus 1 over u squared plus 1 du. And so this is u squared arctangent of u minus, in parentheses, I get u minus arctangent of u plus c. But remember, u is the square root of x. So this is the square root of x squared arctangent of square root of x, right? And then I'm going to go minus the square root of x plus arctangent of square root of x plus c. Let's double check. Yep. Because I'm substituting square root of x for u. But square root of x squared is x. So I get x arctangent of square root of x minus the square root of x plus arctangent of square root of x plus c. And that's going to do it for this video for section 7.5. And we worked all the problems 21 through 29. Okay, thank you.